Hello everyone. Thank you for attending the BAS Electrochemical Webinar 2022 Autumn. I'm Miho from International Sales Team, and I will be the moderator. Today, it will be the second lecture introduced by Professor Masa-aki Haga from Chuo University. This is the second lecture of a series of lectures in the field of coordination chemistry and electrochemistry, introducing basic electrochemical methods and electrochemical applications with a focus on organic complexes. Today's theme is coordination chemistry and electrochemistry, cyclic voltammetry and reactions mechanism at Electrode.
Hello again. This is Masa-aki Haga of this lectures. Today is the second seminar of electrochemical measurements using metal complex as the teaching materials. At the last seminar, I talked about cyclic voltammetry, but I would like to shortly review it. At 3 electrode cell, as shown here, in cyclic voltammetry, potentials apply in the form of triangular wave to the working electrode, WE. The CV experiment recorded the current flowing through working electrode, W, as a function of the applied potential in the circuit. A plot of the current versus potential is constructed, which is called as cyclic voltammograms. The shape of the voltammograms provide insight in the electrode transfer reaction mechanism occurring at the electrode surface. Here is the experimental setup for cyclic voltammogram measurements. To perform a CV measurement, the solvent, substrate concentration, and supporting electrolyte must be selected carefully and depending on the target analyte. Also, the electrode materials, electrode size of the working electrode, which defines the mass transfer of the analyte to the electrode surface, and the reference electrode. The choice is dependent on the experimental conditions and dependent on the analyte. I'll just show you the protocol for CV measurements. When taking the CV measurements, a glass cell is filled with a solution with the supporting electrolyte, and then 3 electrodes are attached onto the cell. Before measuring the CV of analyte, inert gas is blowing into the solution in order to remove dissolved dioxygen, because dissolved oxygen is redox active, so we have to remove dioxygen. Then, in order to check any peaks from the impurity from the supporting electrolyte or solvent, the potentials are scanned. Thus, we know the potential window under the present condition. Here shows one example of 1,2-dichlorobenzene as a solvent and tetrabutyl ammonium tetrafluoride as the supporting electrolyte, which is not commonly used solvent. In this case, the measurement windows can sweep down to a potential of 1600 millivolt on the anodic side, and the cathodic side is minus 1800 millivolt. So this precondition check for the CV is always required. We call it background checking for CV measurement. After being measured the background in 1,2-dichlorobenzene, the analyte is added to the solution, and after the dissolution of analyte, the CV measurement starts. At the beginning, the open circuit potential, where the zero current between the working and counter electrode should be measured, and then the CV curve is recorded for both positive and negative potential directions. In this figure, CV curve of bis trimethylsilyl furalin is shown. In the left-hand side of CV, the anode peak at 1.3 volt versus Ag plus was observed. On the right-hand side, two reversible cathode peaks and additional new anode peak around minus 400 mV as shown in the star marks was seen. This new anode peak could be an oxidation wave from reactant produced as a result of the reduction reactions. Therefore, we should change the sweep potential range from 0 volt to minus 600 mV or 0 volt to minus 1200 mV or 0 volt to minus 1600 mV range. By changing the sweep potential range, we can determine the origin of the star marks peaks, anode peaks. In this case, this star marks anode peak coming from the after the second reduction peak. After finishing all the CV measurement, particularly in non-aqueous solvent case, ferrocene was added as the internal reference materials into the analyte solutions, and CV was remeasured within the analyte. This ferrocene couple is the measure of reversibility for the analyte. So, for the CV measurement of the new analyte, at first, the checking the solvent background, and then by dissolving the analyte into the solvent, CV is measured. Finally, the ferrocene is added as the internal reference, and CV is measured. The obtained peak potentials of the analyte is converted from versus Ag plus to ferrocenium coupled scale. Here shows two typical shaped cyclic protograms. In left-hand side, anode peaks and cathode peaks are observed at both forward and reverse scan, which is called reversible waves. In right-hand side of the CV curves, anode peak is observed at forward scan, but the reverse scan, no cathode peak is observed. We call it an irreversible waves. From these results, how can we analyze the voltammograms and what kind of parameters obtained from these CV waves? Okay, let's analyze the reversible voltammogram. From the reversible voltammogram, as important parameters at forward scan anode peak potentials EPA, and from reversible scan side cathode peak potentials EPC, and their peak current high IPA and IPC are obtained. half-wave potential can be calculated from the half of the potential difference between anodic and cathodic peak potentials. Peak current is obtained from the Landry-Zervik equations, which is proportional to the square root of the scan rate. Therefore, the plot of the peak current versus square root of the scan rate should be a straight line for the reversible systems. Further, the peak-to-peak separation is 59 mV divided by the number of electrons transferred. Ratio of anodic peak current to cathodic peak current is nearly 1. In reversible voltammogram case, the peak potential should be independent of the scan rate. From these three criteria, we can judge the reversibility of the waves. From CV curve, we can read the data and make the table, including their parameters such as EPA, EPC, and E-half, peak separation, IPA, IPC, and their ratios. One example for the tabulation of the CV curve is shown here. By changing scan rate from 50 mV to up to 400 mV per second, in this case, the peak potentials are shifted a little bit. Peak separation becomes smaller at lower scan rate. Therefore, the CV voltammogram is assigned as a quasi-reversible process or involving uncompensated IR drop effect. In irreversible voltammogram, there is no reverse peak observed, and peak potentials varied with the scan rate, which is a sharp contrast to the reversible case. In irreversible case, peak potential is shifted to the negative potential directions, which is shown in these equations. So, if you will report the peak potentials for the irreversible peaks, you should add the scan rate. Furthermore, peak current is proportional to the square root of the scan rate, which is the same as the reversible case. The irreversible wave arises from the first following chemical reactions or slow heterogeneous electron transfer rate at the electrode. So one can get irreversible wave. Please use the faster scan rate or lowering the temperature in order to slow down the following reaction rate. I show one example of ruthenium bis bendoimidazole pyridine compound with longer alkyl chain dications, abbreviated ruthenium DIPOD. The chemical structure is shown here. In acetonitrile solution with tetrabutyl ammonium hexafluoride, the CV shows one reversible oxidation waves, OX1, and two reversible reduction waves, RD1 and RD2, with desorption sharp peaks. For the oxidation peak, when changing the scan rate, the anodic and cathodic peak current is linearly dependent on the square root of the scan rate, which indicates the redox process is diffusion control process. From CV, we can determine the half-wave potential of the ruthenium complex as shown here. When measuring the cyclic voltammetry, a charging current always flows during the potential scanning because the potential is continuously changing. The Faraday peak current is proportional to the square root of the scan rate. On the other hand, charging current is proportional to the scan rate directly. So when the faster scan rate, the Faraday current varied on the charging current. So special care should be taken when the faster scan rate is applied. To perform the CV measurements, we encounter various problems. I pick up several examples from the literatures. First example is the reduction of cobalt cyclopentadienyl diphenylphosphonyl ethane acetonitrile dications. In acetonitrile, when dinitrogen gas is poured into the acetonitrile solution, the background shows no peaks. However, solution contact with the air, the reduction peak was appeared, which arises from the reduction of dioxins. So when you should measure the reduction process, the solution was degassed by inert gas flow. By the addition of cobalt complex in the acetonitrile solution, we can see the two-step reduction waves. However, the solution contact with the air, the second reduction wave disappeared, which means the first reduced species react with dioxins and second reductions and reverse scan peaks all disappeared. The shape of cyclic voltammogram is affected by the solution resistance upon the three-electrode system. When the current flow between the working electrode and a counter electrode, potential drops occurred. Recent potential stack equipped the operational amplifier for positive feedback loops to compensate the solution resistance, even though uncompensated resistance Ru remain between working and reference electrode. The potential that instrument recorded may not be the potential applied to the analyte in the solution due to the uncompensated resistance Ru. The IR drop affects the CV shapes, that is, an increase of peak-to-peak separation and decrease of peak height. To reduce the IR drop effect, three methods are effective. Firstly, the flowing current is diminished by using the smaller size of working electrode. Second, in order to decrease the solution resistance, use the higher electrolyte concentrations. And thirdly, diminish the distance between reference electrode and working electrode. The best way to check the influence of IR drop is to run the voltammogram for well-known cathode such as ferrocenium cathode, and compare the peak separation and scan rate dependence. Sometimes the electrode materials affect the CV shapes. For ferrous cyanide was measured by glassy carbon electrode and platinum electrode. Both electrodes provide almost same CV shapes. However, For the iron-3 reactions in hydrochloric acid solution, glassy carbon shows large peak-to-peak separation and almost irreversible waves. But on the platinum electrode, typical reversible waves shown in the light red line observed. This sharp difference allows from the inert and outer electrode reaction between analyte and electrode, which give the difference CV shapes by just changing the electrode materials. Therefore, it is important to know the different electrode materials can give different voltammograms sometimes. Also, it is recommended to use different electrode when CV measured. Let us summarize the first part of the electrochemical experiment to collect the data from cyclic voltammetry. At first, prepare the electrochemical cell with 3 electrodes setup. Choose the solvent and supporting electrolyte, and then to remove the dioxygen by bubbling the inert gas into the solution. Then background current is measured to check the available potential window in the present solution. After dissolving the analyte sample, the electrochemical method, such as cyclic voltammetry or other methods, are performed to get electrochemical data. Next, from these data, the redox reaction mechanism is discussed by combining the digital simulation technique. In addition, the combination of other physical or spectrophotometric methods with CV data can help the understanding of the reaction mechanism or the synthesis of the new reduced or oxidized species. I'm now moving on the next topics. How to interpret CV voltammograms. Various compounds showing different CV shapes, which indicate the electrochemical reaction takes place between electrode and analyte compound. Here shows 3 different compounds in this slide, which shows different CV shape in the bottom. So from these CV data, we have to consider the reaction mechanism of the redox reaction occurring at the electrode. Once the electron transfer of analyte occurred at the electrode, there are several homogeneous chemical reaction pathways, which is summarized in these figures. Reversible electrode reactions of analyte A-B couple takes place at electrode solution interface. When the reduced species B is reactive, a follow-up reaction proceeds. Reaction mechanisms in electrochemistry are frequently labeled by strings of letters signifying the reaction step. E represents electron transfer at the electrode, and C represents homogeneous chemical reactions, and the sequence involving decay of the product after the electron transfer, showing such as EC reactions or EE reactions. In the case of EC mechanism, after the reduction of A to B, the reduced B is converted to species C by chemical reactions. We call this reaction mechanism as EC mechanism. In EE mechanism, the one electron reduced species further reduced to a doubly reduced or doubly oxidized species C. We call it EE mechanism. In ECE mechanism, after the EC mechanism, the resulting product C is reduced to the species D. This is called ECE. In special type of EC mechanism, the species Q, which is electroinactive, react with the electroproduct B to regenerate the starting A. As a result, the species Q is converted to P by electron mediation of AB couple. This is called catalytic mechanism. As shown in this slide, each mechanism shows characteristic CV voltammogram, so we can judge what kind of electrode reaction occurred at the electrode from CV voltammogram. So we will show you the detail of each mechanism from the viewpoint of the voltammogram shapes. First of all, let us consider an EC reaction mechanism. The electrode reaction produced the reduced species B. However, this reduced species converted to C by the follow-up chemical reactions. Therefore, the shape of the voltammogram varied greatly depending on the homogeneous reaction rate K. Here shows the shape of CV and the distance dependence on concentration profile of each chemical species from the electrode. The diffusion equation at the electrode, which determines the current, are shown in here. The first order rate constant K is involving in the diffusion equations. Increasing the homogeneous reaction rate K, the reverse peak height becomes smaller because the concentration of reduced species B decreased by the reactions. This is a characteristic of CV shape of EC mechanism. When you get the CV shape of the second law or third shapes, you should try two things. At first, use the faster scan rate to overcome the homogeneous reaction rate. You'll have a chance to get the reverse peak. Further, by lowering the measurement temperatures, you can slow down the follow-up chemical reaction. So, we also have a chance to get the reverse peak. Once you will observe the reverse peak, the homogeneous reaction rate can be estimated. This slide shows the change of CV shape from the reversible to irreversible process by following up reactions from the digital simulations. The important parameters to determine the CV shape is the ratio of the first order rate constant K to the potential scan rate V in these equations. By increasing the homogeneous reaction rate K under the same scan rate, the reverse peak current becomes decreasing. Considering the parameter lambda, which is defined on these equations, when lambda is greater than 1, anode peak disappeared. In this slide, when lambda is 0.257, we can see the reverse anode peak as shown in this circle. When you'd like to observe the reverse anode peak, homogeneous rate constant as 1 per second at the scan rate is 0.1 volt per second will be enough. However, the reaction rate constant becomes 100 per second, 100 larger than previous one, then scan rate 10 volt per second is required to obtain the small reverse anodic peak. Now, I show you one example of EC mechanism as a case study reported in the literatures. The oxidation of iodo-pentacarbonyl chromate anions in acetonitrile. This chromate complex shows two successive one-electron oxidation waves. The first anodic peak is reversible because of appearance of reverse cathodic peak. But the second peak revealed no reverse cathodic peak at room temperatures. When measured temperature was lowered at minus 60 degrees, the second peak becoming reversible. This result indicates the second oxidation process took place by a typical EC process. That is, iodo-pentacarbonyl chromate anion was reversibly oxidized as one electron oxidation process, and then two electron oxidized product, iodo-pentacarbonyl chromate cation, was unstable, accompanied by the decomposition reactions. So this is a good example how to tackle the question of EC mechanism. Another EC mechanism of organometallic tungsten complex, the iodo-pentamethyl cyclopentadienyl nitrosyl tungsten complex. At scan rate of 0.13 volt per second, two cathodic peaks were observed at minus 0.6 volt and around minus 1.2 volt. The first cathodic peak current was higher than the second one. Furthermore, the reverse anodic peak is smaller, indicating the first reduction was accompanied by the follow-up chemical reactions. When first the scan rate of 2.64 volt per second was performed, the first cathodic peak showed the clear anodic peak, indicating reduction, and the second cathodic peak was disappeared. This indicates the second cathodic peak derived from the reduction reactions due to the resultant product produced in the first reactions. By plotting the ratio of the first cathodic peak current versus anodic peak current to the scan rate, the ratio becoming increasing, resulting in the reversible process for the first reduction. As a case study 3, I'd like to show you the recent electrochemical study of EC mechanism about cyclopentadienyl 1,2-bis diphenylphosphonyl ethane acetonitrile cobalt dications, as shown. The structure is shown in this slide, which is relevant to the electrochemical dihydrogen evolution catalyst. In acetonitrile solution, two-step one electron reduction waves were observed at minus 0.51 volt and minus 0.93 volt versus ferrocene couple. However, in dichromethane solution, two cathodic peak, but the first wave becoming irreversible because cobalt 3,2 reduction facilitates the dissociation of acetonitrile in dichromethane solution. The second reduction process occurred at cobalt 221 unsaturated complex as shown in these equations, which induced the protonation to form cobalt hydride complex. Therefore, the electrochemical behavior of this cobalt complex can be interpreted by the electron transfer followed by the ligand loss and the electron transfer and the unsaturated cobalt complex. The addition of acetonitrile into the cobalt acetonitrile complex in dichromethane solution, the first irreversible wave becoming reversible and shifted to the negative potential directions and described by this equation. And we can get the acetonitrile dissociation length constant Kd was obtained. The resulting cobalt hydride complex is it for the hydrogen evolution reactions. To prove the hydride formation, the CV change was monitored by changing the acidity of organic acid. Two examples with different acid for cyanoaluminum and benzoic acid example is shown in this CV change. According to the peak shift for EC mechanism in this equation from the peak shift by the concentration of acid, we can calculate the K observed, which is the protonation reaction rate, which provides us the quantitative information for the kinetics of hydride complex formations. Today, I talk about the protocol of cyclic voltammetric measurements and show you how to analyze CV data. From the CV data, diagnostics of reversible or irreversible wave is discussed. There are many reaction mechanisms at the electrode, which provide different voltammogram shapes. Today, I show only the EC mechanisms. So in my next talk, I'd like to expand further and discuss other electrode reaction mechanisms such as EE, ECE, and catalytic mechanism and their CV shape. See you next time. The perfect reference book is Alan J. Bird textbook. A third edition has recently been released. The book is now about 1.3 times as thicker as the second editions, as shown in this slide. In addition, Compton and his colleagues' Understanding Voltammetry is a good book to learn about CV from undergraduate, and Kissinger's book is a bit outdated, but is a good reference for basic electrochemical measurements. Zanero's book describes the descriptive chemistry of CV from the viewpoint of inorganic complex. Oldham and Bond's book is a textbook on electrochemistry that can be read from undergraduates. Number 5 and 6 are the good reviews that seek the basis we discussed today.
Thank you, Professor Haga. If you have any question regarding to the lecture or other topics, you can contact us. In addition, the movie of a variety of topics you can watch here in the BAS channel, which you can follow and have access to the latest news, including the past webinars. The next webinar we are working out to have for December. It will be the third lecture in the field of coordination chemistry and electrochemistry. For today, thank you and have a nice week.